Everything in our universe is made from fundamental particles. Its immensity is filled with microscopic mysteries. For 7 years, Cern scientists have been working to unveil its secrets, making it the world's largest center for particle physics.
Willkommen bei Rätsel der Wissenschaft, dem Standard-Podcast über die großen Fragen der Menschheit. Ich bin David Rennert.
Und ich bin Tanja Traxler. Wir beschäftigen uns jeden Mittwoch mit den ganz großen und ganz kleinen Mysterien in unserem Universum.
Heute gibt es bei uns eine Live-Folge zu hören. Wir haben die Cern-Direktorin Fabiola Gianotti getroffen und mit ihr über den Ursprung des Universums und die großen ungelösten Fragen der Teilchenphysik gesprochen.
Diese Folge ist bei der langen Nacht der Forschung in Wien aufgezeichnet worden. Und damit ihr euch nicht wundert, Fabiola Gianotti ist ja eine italienische Physikerin und wir haben mit ihr auf Englisch gesprochen.
Viel Spaß mit der Folge. Give a warm welcome to our guest today, Fabiola Gianotti.
Thank you very much.
She is the Director General of Cern.
Yes,
Yeah, please give a big hand to Fabiola. Welcome to the show.
thank you. Thanks.
This year, Cern is celebrating its 17th birthday, and in the last decades, we have seen numerous scientific and groundbreaking discoveries. It is the largest machine on Earth, located nearby Geneva in Switzerland, and it has fundamentally changed our understanding of the universe and the very constituents of matter.
Fabiola is herself a physicist and was and is involved in many of the great discoveries at Cern. Most well known and most important, of course, is the discovery of the Higgs boson in 2012. She's in Vienna today as a guest of the Austrian Academy of Sciences and the Austrian Federal Ministry of Science and Research. And we are, of course, very happy to have you here on board as part of our show.
Thanks so much for having me. Thank you. Thank you. Very happy to be here.
Fabiola, it's now already more than 10 years that the experimental confirmation of the Higgs particle could be achieved. You were also a leading scientist in this endeavor. Still, Higgs physics and the measurement of the Higgs particle is of relevance today. There are many experiments to do ever more precise measurements. Why is it not getting boring around the Higgs particle?
Thanks for the good question. So today we have discovered and observed experimentally some 17 elementary particles. And the Higgs boson is very special, is completely different from the other 16 particles. In terms of its properties, we call them quantum numbers in physics. So it has very special features. It interacts with a different force. It's not the same forces that the other that we know today, gravity, which acts on astronomical, big scales, the weak force, the strong force, and the electromagnetic force. It brings a new type of force and is a particle that is related to the very first instance of the universe. When I say very first instance of the universe, the universe had origin from a big explosion, which took place some 13.8 billion years ago. And some 10 to the minus 12 seconds after this big explosion, so in millions of a second after the Higgs boson, the so-called Higgs field, so field like the electromagnetic field, but different in features, settled in the universe. We don't know why, we don't know how, but this field appeared in the universe, which was otherwise before that empty. And it is thanks to this phenomenon that matter formed in the early universe, the matter of which we are made of, so atoms, chemical elements. So without the Higgs field and the Higgs boson, we will simply not be here. And also the Higgs boson is related to the fate of the universe, because we think today, based on the feature of the Higgs boson and other particles, that the universe is not in a stable state. It's in a metastable state and could decay in a more fundamental state, not tomorrow, in some billions years from now. So it should be relaxed. Yes, we are safe. And so the Higgs boson is really related to the very, very initial state of the universe and most likely to its fate. We have studied it over the past 10 years, but there is more to know and understand. It's really very special particle.
There's still a lot to do with the Higgs boson. And we have this beautiful standard model of particle physics, which is kind of like the ingredient list of everything there is in the universe that we see. But it's not the whole story. We know that there is something beyond, some physics beyond this standard model. How can the Higgs boson help us get on the track to find the physics beyond?
So thanks for a very good question. So what we call the standard model, which is a little bit of, model is not the right, and call it standard model, but model does not really give credit to this fantastic theory that describe most of the things that we see. However, the problem is that the thing we do not see, but we know they exist. So an example, when we look at night, we look at the beautiful sky, we see stars, galaxies, etc. What we see is only 5% of what is out there. Means that galaxies and stars, which are made of the same type of matter we are made of, atoms, chemical elements, they are only 5% of the universe. The rest, 95%, is made of forms of matter and energy that we do not know. And we call them dark matter and dark energy. These are very profound questions because we are missing something really big. It's not just, a few percent. It's something very big that we do not understand. And the Higgs boson may be related to the dark matter, but also is clearly related to other mysteries in fundamental physics today. We don't understand its mass, why it's so light. We don't understand today the pattern of the elementary particles. I said we have, 17 particles. They seem to have masses and mix in the way they do, couple with each other, which are quite mysterious. And the Higgs boson, again, may be the clue to understand, the key to understand these mysteries. So the Higgs boson is considered to be today as a discovery tool, something that can allow us to answer these open questions.
Besides measurement on the boson and Cern, there is also a so-called antimatter. Oops, now the sound is back. Antimatter factory located. Fabiola, what do we know about antimatter so far? And what are the still big open questions concerning antimatter and also the relationship of matter to antimatter?
So another important question, another big mystery. So today, the universe is almost exclusively made of matter. There is very little antimatter, 1 atom out of billion atoms or so. And we do not understand why. So first of all, antimatter sometimes is depicted in some movies, some books, like something very dangerous. Is not dangerous. Is very nice, is like matter. But just to oversimplify, antimatter is matter with the opposite sign. It's not so simple, but okay, let's simplify. So if I take an electron, the antiparticle of the electron is a particle which has exactly the same features of an electron, except the charge. An electron is negatively charged. The anti-electron, which is called positron, has a positive charge. So this is, again, oversimplifying. So there are some physicists in the audience, so I should maybe say this clearly. Okay, so the problem is that we think that in the early universe, matter and antimatters were present in several proportions, several amounts. But today, the universe is almost exclusively made of matter, with very little antimatter. Thank goodness, because matter and antimatter have this unpleasant feature, and when they get together, they annihilate and gives rise to energy. So if I take an electron and a positron and I make them interact, they disappear into energy. So again, we will not be here if matter and antimatter had persisted in the universe in similar amounts, because all the matter and antimatter would have disappeared, and so we will not be here. So something happened. We don't know what. So one of the things that is important to do is to study matter and antimatter in very, very high, in all details, with very precise measurements, and see if there is any difference in their behavior. And this is what we are doing at Cern. We have the only dedicated antimatter factory in the world, where we produce antiprotons, which are the antiparticle of protons. We combine them with anti-electrons, and we form atoms of anti-hydrogen. And then, no, hydrogen is the simplest atom. Then, by making spectroscopic measurements, so understanding how the hydrogen atoms behaves, the energy levels, etc., and comparing with anti-hydrogen, we try and see if there is any slight deviation that could give us a clue of what happened in the early universe. We also do gravity measures. We see if they fall in the same way, and first results show that antimatter also falls, doesn't go up, goes down. It was sort of expected, but it's always good always to measure and confirm them. So actually
you are producing the most rare material.
Absolutely. Let me stress that, by the way, that institute here in Austria, of the Austrian Academy of Science, are very much leading efforts at Cern, both on, we discussed the Higgs boson and the energy frontier, but also antimatter and understanding atoms. So Austria is really at the forefront of the investigation of the most crucial open question today.
Let me just quickly jump back to the dark universe. You mentioned it before, dark matter, dark energy. It's a really fascinating topic if you think about it. If you look up in the sky, if you look out through telescopes, everything you see, all the stars, all the planets, all the nebula, everything actually, the galaxies.
It's just 5%.
It's 5% of everything that there is. And all the rest, the 95%.
Exactly. So in particular, dark matter is responsible for holding galaxies together. There is 7 times more dark matter than matter. So matter is typically 5%, dark matter is typically 25%. So dark matter is mostly the dominant component of matter in the universe and keeps all the galaxies together. Dark energy, on the other hand, is responsible for the current accelerated expansion of the universe. So the universe had origin from this big explosion. You can imagine like after an explosion, then at some point, because of gravity, there will be an implosion. So the various planets, celestial bodies, etc., will at some point bring the universe to implode. But some 5 billion years ago, the universe started to expand again in an accelerated way. And we think that so there must be a force that counterbalances gravity and makes the universe expand. And this is dark energy, is a scalar force, so is a pressure that pulls the energy, pushes the energy, the universe apart. Again, we don't know the origin of this force. So it's sort of embarrassing that we know so little, but so exciting that we still have so much to learn. And of course, we have made also a lot of progress. So we know a lot today, but still we are missing something big.
Yeah, at least we know what we all don't know. So dark matter and dark energy are both very prevalent in the universe. Why is it that in our very best research facilities like at Cern, they didn't show up yet? What is your guess?
It's a very good question because, we don't know so today we know some of the open questions. These are the known unknown. So we don't know the composition of dark matter and dark energy, but we know they are there. There may be also unknown, question that we have not understood. And doing research and doing physics, actually, and doing scientific research is also primarily understanding what are the right questions to ask. So we don't know where nature has put the answers to the open question. We don't know at which energy scale, for instance, we will understand the problem of particle masses. We don't know how heavy is dark matter. It can be very, very light, it can be very, very heavy. So that's why nowadays the best thing to do is to deploy the variety of approaches that particle physics, astroparticle physics, and other fields have developed, thanks also to incredible progress in technologies, in detector technologies, accelerator technologies, computing technologies, which, by the way, also have an impact on society, and deploy all these different instruments to try and see and capture dark matter or understand the dark energy. But research is really exploring the unknown. And this is what we do today. And this is also the charm, if you want, of research.
Wir machen eine kurze Pause und sind gleich wieder zurück.
Guten Tag, mein Name ist Oskar Bronner. Im Standard liest man seit 35 Jahren das, was man wissen muss. Und nicht das, was man glauben soll.
Guten Tag, mein Name ist Robert Diesenreiter. Und genau deshalb weiß ich, warum ich für den Standard arbeite.
Der Standard, der Haltung gewidmet.
Development in technology, in accelerator technology is a key word for me now, because Tanya mentioned before, it's the biggest experiment we have on this planet is at Cern. It's the Large Hadron Collider, LHC in short. It's about 27 kilometers long, and it led to many big discoveries. But there are plans being drawn up to build an even bigger successor to this.
Yeah, so let me first say, because we mentioned technologies and application to society, that the technologies developed at CERN have found and continue to find huge application in society. The World Wide Web is an example. So Tim Berners-Lee, the inventor of the web, was a CERN staff when the web was developed back in 1989. And it's interesting to see how some of these breakthroughs really come from fundamental research. Accelerators at CERN are used today to treat cancer. Austria actually has a big center, Medostrom, that is used to the treatment of cancer with protons and light ions, like light carbon ions. And this Medostrom has been built with the CERN technologies. CERN technologies today are used to help society protect the planet, climate change, and more sustainable energy, etc. So these technologies really have a huge impact on society. So now, in order to understand, to address the open question, we need to study the Higgs boson in more details. So this is one way of exploration, because it can be, we think it's a discovery tool, but also explore the next energy frontier, because many of the answers to this open question can come from the next energy frontier. So we need for this bigger colliders, so bigger ring, and we need to push the technologies for magnets, technology for accelerating structures. So again, a big jump in the technologies and a big jump into the capabilities of discoveries.
Do you want to share a little more details about this future circular collider where physicists currently working? How would it look? What would it allow to do?
Right. So thanks so much. So at the moment we are doing the feasibility study. Feasibility means geological feasibility. These are big underground tunnel. It means environmental impact, because of course nowadays research must be green. You can't imagine of any instrument which is not fully respectful of the environment. So very, very small emissions or zero emission or close to zero emissions, but also a project that develops technology that could help society to protect the environment. And in this sense, this future circular collider are many technologies like that. So it will be a bigger ring. The current ring is 27 kilometers. The future one will be 90 kilometers and will allow us to study the Higgs boson in all details and to make a big jump in energy. China wants to do exactly the same thing. So there is competition, because today Europe, thanks to CERN, has leadership in fundamental physics, in particle physics. And of course, there is a competition now with China that may bring this leadership, and all the technologies that go with the field, they may bring them to China. So we have, of course, to try to keep this in Europe. But at the moment, we are just doing the feasibility study, financial, technological, environmental, geological, etc. And then we will see if in a few years from now, the project is approved or not.
What could be a possible time frame for this?
So approval may come before the end of this decade, so time scale of 2028. Construction may start at the beginning of the 2030s and operation in the mid-2040s. It looks like a long, much farther in the future, but keep in mind the CERN is running the Large Hadron Collider. We are now upgrading the Large Hadron Collider, and operation will end at the beginning of the 2040s. So we cannot have two colliders at the same time. We have to, so the next one will start maybe in 2045 or so. It's a big technological challenge. But of course, the impact on society will be, and the socioeconomic benefits to society will also be huge. So it's probably worth it, not only for physics, but also for society.
Yeah, let us stay with the societal impacts for a moment. You have already mentioned the World Wide Web and also the medical applications, also here in Austria with Medostrom. What are further advances of these technologies that are being developed on the go when operating such a facility?
So one example is, of course, CERN, the Large Hadron Collider today, but also a future collider will need a new generation of superconducting magnets. And you know that superconducting materials are materials that allow to carry huge currents. For the LHC on the Future Collider, we're talking about 12 to 20,000 amperes. So it's enormous amount of current with no losses and with very small cables like that. With normal copper, you will need enormous. So being able to transport electricity with no losses and with very small cables is absolutely essential for sustainability. Not to waste energy, but also if you think, for instance, of clean air transportation, electrical air transportation, you cannot have big cables. They have a huge weight, so you need very light cables. So Cern, for instance, today is collaborating with Airbus to develop these superconducting cables for clean air transportation. So this is an example of the technologies that fundamental research can push because of our needs, and then can have a very, very important impact on society.
There's another side of impact to society. We mentioned before it's the 70th birthday of Cern is this year. So when Cern was drawn up this project, it was after the Second World War,
Yes.
in the middle of the Cold War, this huge project of scientific collaboration, international, mainly in Europe, but actually international. So what is your take on this? How would you reflect on this today? How important is
Thank
it
you.
to have a project like this, also in times like we unfortunately see today, in times
Thank
of
you.
crisis and international conflict?
Thank you for this very good question. So Cern is a unique institution in the world. Many other centers or fields have tried to clone it, but it's not that easy. And it's not that easy because what you said, the very peculiar historical moment when Cern was founded. It was 1954, and some visionary scientists and politicians understood that it was time for Europe, after the disaster of the war, to bring back scientific excellence. During the war, many brains, many scientists had left Europe due to, why? To go to the United States or to Russia. And so there were few brains left in Europe. So Europe was not really still at the forefront of research. So they understood that it was time to bring back scientific excellence in Europe. And they understood that the recovery, even the economical and social recovery of Europe, also goes through investment in fundamental research. It's a very modern view. This was one part of the vision. The other part of the vision was science is a glue, because science is universal. Universal because the laws of physics are the same in China, in the United States, in Austria, in Italy, everywhere on Earth. So it's based on fact. So it's universal, but also unifying because the wish and the passion for understanding how things work, these are shared values common to all of humanity. So science can be a glue that connects people in a fractured world. And this was the world after World War II. It was in a very special geopolitical situation like today, by the way. And so they understood that science could help foster peaceful collaboration. Hence CERN. 12 member states signed the founding convention. Today we have 23 member states. We will become 24 this year, so we double the number of member states. We have 11 associate states. We have several observers, and CERN was able to bring back leadership in particle physics to Europe, so the founding fathers will be very, very, very happy, but also to extend this role of peaceful collaboration well beyond Europe. Today, CERN hosts 17,000 scientists from all over the world. More than 110 nationalities are represented. So it's a big success. Now people talk about a CERN for quantum, a CERN for artificial intelligence, a CERN for climate change. It's really a model, and I would like to stress that CERN is so successful primarily because of the sustained support of the member states over the decades, and Austria is one of the member states, so I am grateful to Austria. This support over 70 years allows CERN to carry out projects that no single country could have carried out, and to revolutionize fundamental science and also technology. And another important impact on society that CERN has beyond the technology is people, the human capital. We have so many scientists, but at any given time, we train permanently 4,500 people, including physicists, engineers, and technicians over a huge number of domains, from electronic to mechanic, cryogenics, vacuum. only a little fraction of these people stay in research in particle physics. Most of them go to industry, and we know that industry and society today needs talents in STEM, science, technology, engineering, mathematics. So we contribute to forming, to training these people.
For many of these reasons that you've just mentioned, it's always a very great experience to visit Cern. Now, this year is a very good opportunity also with all the many festivities that are going on. Also, a couple of months ago, a new outreach center was opened. To what kind of events are you looking forward, and what can people, the general audience, also see and visit during this festive year at Cern?
Yeah, thanks so much. So Cern is a really nice place to visit because we have several facilities that the public can visit. It's all free. You don't pay anything when you come to Cern. By the way, the technologies that we develop, like the World Wide Web, they are transferred to society free of charge at zero cost. This is enshrined in our funding convention. We are funded by public money, and whatever we develop is available to everyone. But as you said, actually, a few months ago, in October last year, we inaugurated a new center for scientific education and outreach for the general public of all ages, starting with children, 5-year-old children, up to the more senior people. It's called the Science Gateway. It was inaugurated on the 7th of October and opened to the public on the 8th of October last year. And since then, so 7 months, we have welcomed 250,000 people. We get 1,500 to 2,000 visitors a day. So please come. You will be able to see many things that we operate underground, and you cannot visit underground at any moment because we operate our facilities. So the tunnel is not, and the experiments are not open to visit, but you will see many of the objects, the real objects, available in the Science Gateway. So I hope that many people will come.
So when will be the next opportunity to visit underground, to go to see the accelerator? When is it?
A limited number of visits are possible at the end of the year. Between December and March, we will be stopped the accelerators and the experiments for the yearly maintenance. But the best time will be during our long shutdown when we have open days. And typically we have, the last open days, we welcome in a couple of days 75,000 visitors from all over the world. The next one will be during the next shutdown, which will start in 2026. So it will be an opportunity for thousands of people from all over the world to visit and go underground.
That's really great. This podcast takes place at the Postsparkasse. We also call it the House for the Arts and Science. At Cern, you have a very renowned program that combines the arts and science. Why do you think that it's important, also for both sides, to do this interdisciplinary endeavors?
Because science and the arts are the same thing. They are the expression of the creativity, curiosity, fantasy of a human being. So I don't understand, when science and arts are put in separate silos. They are part of us being human being with a brain which always wants to understand how things work, which wants to create new things, which want to explore new ideas. And so Cern has this program, Arts at Cern, which was founded more than 10 years ago, where we, for instance, one of the things we do is to host artists at Cern. They spend some time with us, with scientists, and they try to find commonalities. The question that we ask ourselves about the structure of the universe, this same question, of course, inspire many artists. Some of the technologies we develop, some of our instruments are beautiful, although they've not been built to be beautiful, but to be functional. But they're so beautiful, and so they inspire also the artists. And so we try to foster links and relations between the two, and we see that there is a lot of positive reaction to this.
Very nice.
So it clearly doesn't get boring in particle physics.
No.
With inspirational collaborations like this and the big mysteries that we briefly talked about, like antimatter and the dark universe. We will for sure follow up the science of Cern, also in our podcast, Rätsel, Wissenschaft. Fabiola Giannotti, thank you so much for being
Many
today
thanks
with
for
us.
the very good questions, and I like your T-shirt, standard model. Thanks for the very good question, and thanks for being here.
Thank you so much.
Thank you all for coming and for being here with us tonight. We've closed this round with an open invitation to Cern, as you have heard. And also a special thanks to our producer, Christoph Neuwirth, and of course everyone involved to make this happen here at the Postsparkasse.
Thank you so much.
Vielen Dank, dass ihr heute wieder dabei wart und damit verabschieden wir uns jetzt endgültig in die Sommerpause. Im Herbst geht's dann weiter mit Rätsel der Wissenschaft, ab Oktober überall, wo es Podcasts gibt. Bis zum nächsten Mal.
Ciao.
Hat Österreichs Politik ein Korruptionsproblem?
Wie wird der Ukraine-Krieg enden?
Und warum wird alles immer teurer?
Ich bin Tobias Holub.
Und ich bin Margit Ehrenhöfer.
Wir stellen die brennenden Fragen unserer Zeit.
Und die Standardredaktion liefert Antworten.
Im Thema des Tages, Montag bis Freitag um 17 Uhr, überall, wo es Podcasts gibt.